In this video, we're going to look at the growth of an IRA. Now, you may have heard that you should save for retirement when you're young. And so in the graph that's at the top here, I want you to see a couple of things. One person started saving for retirement at age 25, and you see that the growth here in this graph is really, really tiny. So they're not saving a ton at that age, but they are saving something. The other person started at age 35, and again, but saving a little more, grows definitely faster. But at the end game, at age 70 for both of these individuals, the person who started early has so much more. So these top images are to help you remember this principle that it really does pay to start saving for retirement early on so that you have that nest egg when you're ready to retire. The savings that we're looking at are really annuities, and from your textbook, hopefully you understand an ordinary annuity is just anything that you're making the same payment to on a regular basis. So we're going to look at a very involved problem, and we'll look at it in several different parts, and we'll use our annuity formulas. We'll also use the interest formula to just work through all the questions that are there. So here is our problem. I'm not going to read all of it to you now, but we're going to deal with just the first paragraph. So we're dealing with Jane. And we see that she deposits $2,000 annually into a Roth IRA that earns 6.85% compounded annually. So I don't have to adjust my interest rate because it is compounded annually. And then due to a change in employment, these deposits stop after 10 years, so that 10 years is really important. However, the money's going to continue to earn interest for 25 more years, and so that's where we're going to move from the annuity formula into the interest formula. So let's take a look at Jane, and our goal is to figure out how much is in the account when Jane retires. So I have down here the future value, and we want to calculate what this account is worth in the future. So that future value is the piece that we don't know. And so what we do know, so let me just fill in my formula here. Future value is equal to the payment. Well, the payment we know is what you're depositing. And so in Jane's case, she's putting in $2,000 annually. And then we have 1 plus interest rates we know we have to change to decimals, so 0.685. The end value is the number of compounding periods, and this is annual, and it's happening for 10 years that she's making these deposits of $2,000 a year. And then we'll subtract 1, and we divide the second part here by the interest rate, so 0.0685. And now, your graphing calculator will handle all this. Be real careful with how you type it in. So inside the parentheses, you can do this math in your head, 1.0685 to the 10th power. Subtract 1, get that answer. Divide and multiply. So doing all that on my graphing calculator, and you can pause here if you want to type it in yourself and make sure that you get the right answer. The future value of this account, so when she's done at the end of the 10 years, is $27,437.89, and I rounded that to the nearest cent. Now, the next thing that happens in Jane's life is she's no longer contributing to the account, but it's still going to earn interest for another 25 years. So I'm going to go to the compound interest formula. It is compounded annually, and the principal, the investment, is this ending value when she stopped contributing to it as an annuity. So the amount in the account is equal to principal $27,437.89. In my parentheses, I have 1 plus my interest rate, which has not changed. And my N value, the N on this is now the 25 years. So I'm almost out of room. I'll try to squeeze that in. Again, your graphing calculator will handle this really well. So you type in the $27,437.89 times, you can do the math in the parentheses here in your head, and then use the caret key to get this exponent. And so we'll have a final amount in this account of $143,000 785, and rounding to the nearest cent is going to give me 10 cents. So be careful with that rounding because there's a 9 that rounds up then to a 10. And you may want to jot down this number. This is the ending amount, and we're going to use that number when we look at Mary. So I'm going to wipe my slate clean, go back to my original problem. I again included a formula, and this time the formula that I included is still that annuity formula. However, this time we're asked about the payment, so I have reworked the formula, and it's right there in your text, so that I can solve it for the payment. So we're looking at the second paragraph here about Mary, Jane's identical twin sister. She is starting her Roth IRA 10 years later. So like that original graph, one of them starting at age 25, one starting at age 35. And for this, she's going to have the same interest rate as her sister did. And the question is, how much must Mary deposit each year for the next 25 years in order to have the same amount at retirement? So we want to figure out the payment, so that's my unknown. The future value, well, I want it to be the same amount that Jane had at retirement. So I'm going to fill in that amount from the previous slide. So $143,785.10 is how much we want this to be worth. Our interest rate, we said we're using the same interest rate, so 0.0685. And substituting values into the denominator, 1 plus 0.0685 to the n power. Now we have here that this is going to happen for 25 years. So all those 25 years while Jane's money is just sitting there, Mary is contributing. Again, I'm going to have this calculation done on my graphing calculator. So I can type this fractional part in, just be careful with your parentheses, so 0.0685 divided by, and then put this whole denominator in parentheses, so you're dividing by all of it. So I'll put 1.0685 to the 25th power minus 1, and then end my parenthesis out here, and then take that answer times this amount. From that calculation, and you may want to pause the video and try it to make sure that you're good with typing that on your calculator. The payment for Mary is going to be $2,322.73, and that's an annual payment. We'll notice up here at the beginning of our problem that Jane was originally depositing $2,000. So in some respects, Mary's only depositing slightly more, $322 more per year. However, key difference here is that Jane deposited that $2,000 for only 10 years. And Mary is going to be depositing that $2,322.73 for a full 25 years. So that leads us, and again, you may want to write down numbers before we address the last question because I am going to clear the slide here, to what is the difference in the amounts that Jane and Mary deposit towards retirement. Both ladies are ending up with the same final amount, the $143,785.10, but the amount that they contribute is vastly different. So we'll look at Jane first. What does Jane contribute? Well, Jane is contributing $2,000 a year, so $2,000 for 10 years. And so we can do that math in our head. Jane is contributing $20,000 towards her retirement, ends up with $143,000. And Mary, on the other hand, we had calculated needed to make payments of $2,322.73, and she needed to do that annually for 25 years. So I'm going to plug all that into my calculator, and I find out that Mary contributes $58,000, 68 and 25 cents. Wow, what a difference. So if I subtract the two, 58 minus 20,000 here. The difference, which is what the question actually asks, is $38,068.25. So both ladies end up at the same place, but because Mary started later, even though she had the exact same interest rate, she ends up contributing a lot more of her money to get to the same place that Jane is. So I hope that you found this video helpful in using your annuity formulas, seeing where to plug in the numbers, and then be very careful with the typing the formula on your calculator and using the parentheses at the right place.